vertical wall carries uniform positive charge at the surface. This produces uniform horizontal electric field perpendicular to the wall. A small positively charged ball is suspended in equilibrium from the vertical wall by the thread of negligible mass. The charge per unit area of the surface of the wall is sigma. It can be shown that the electric field strength due to the charge of the wall is given by this equation sigma over 2 epsilon 0. Demonstrate that the units of the quantities in this equation are consistent. Okay, meaning we prove units are the same on both sides. The unit for the electric field is volts per meter, or it also equivalent to another unit is Newton per coulomb. Force per charge, okay, charge, unit charge. So we will take the unit of sigma and epsilon and plug into this equation. Sigma has the unit, its meaning of sigma is the amount of charge per unit area, meaning the density of charge. Okay, so sigma has the unit of coulomb per meter square. Okay, and then divide epsilon 0. The unit epsilon 0 in the booklet here is coulomb square per Newton per meter square. Coulomb square per Newton per meter square. Okay, so you see that meter square cancel each other out, and coulomb, so that equal to coulomb minus 1 and Newton, so which is the unit of electric field. Okay. Okay, so just write an equation like this, and you got 2.
Okay.
Okay, take the unit of epsilon 0 in the booklet.
Yeah.
And the meaning of sigma is charge per meter square. Charge coulomb. Question B, the thread maximum angle 30 degrees. The ball has a mass of 0.025 kilograms. Determine the horizontal force that acts on the ball. Can you do that? Using the equilibrium conditions for the ball. Equilibrium condition, meaning the net force, the total force acting on it is 0. The first force, of course, always the weight mg. Okay. The second force is the tension on the string. You should draw the tension so that its vertical component, the tension, the vertical component here, will be equal exactly to the weight, so that it cancels the weight and the ball doesn't move up or down. Okay, this is the tension. And the third force is the electric force of the wall. The sum of the 3 forces is 0. Okay.
Yeah.
Let me like trying to draw a triangle. This force, that is mg, w weight. Okay. The second force, F, and then the tensions that make a 0 triangle. Okay. The sum of the forces is 0. That is the condition for the equilibrium system state. Okay, equilibrium. You got it?
Yeah.
So, determine horizontal forces that act on the ball. Let's draw the diagram here again. You don't need to draw it in the answer when you do the real test. The way mg, the electric force, which is the charge times the field strength, and then the tension in this direction, tension. The angle, what angle? 30 degrees. So I draw it like greater than 30, but anyway, taken it to be 30 degrees. Okay. Determine the horizontal force that acts on the ball, meaning this one, QA. Okay. So from this diagram, we see that We don't know the tension, therefore we must use the weight mg. We know the mass of the ball, 0.025 kilogram umg. So we have the adjacent mg and the opposite QE, which we need to find. Opposite of adjacent is tan, okay? Tan 30 degrees equal QE, which is the horizontal force, which we need to find, over mg. And therefore, this horizontal force, QE, is the mg times tan of 30 degrees. Okay. The weight is 0.025, G 9.8, and tan of 30 degrees. Use the calculator. And it will be
negative 1.57.
0.14, right? Newton.
Oh, never mind.
Okay, 0.14. Yeah, we take two significant figures, 0.14 newtons. That is how to answer this question, okay? Equilibrium condition, meaning the object doesn't move. The total force is 0. The charge of the ball is 1.2 times 10 to the negative 6, determining sigma. We already have that the field E given above the equation sigma over 2 times epsilon 0. Okay, so to find sigma, we need to find E. We already have the force is the charge of the sphere, the ball, multiplied with the field, and therefore we can find the field. Okay, the field is the force 0.14 divided by the charge of the ball, which is 1.2 times 10 to the negative 6. And then using this E equals sigma over 2 epsilon 0, we find sigma. Okay. 0.14 divided by 1.2. Then 1.2 also. 1.2 times 10 to 5. Okay. This unit volt per meter, and then finding sigma. Sigma will be this E multiplied with 2 times epsilon 0, 1.2 times 10 to 5 times epsilon 2 times epsilon 0 is 8.85 times 10 to negative 12. Okay. This thing multiplied with 10 to the power 5, meaning 5 zeros, times 2 times 8.85 times 10 to
2.12 times 10 to the power negative 6.
Negative 12. 2.0. Yeah, and how many? 1, 2, 3, 4, 5, 6, 7, negative 7. 2.0 times 10 negative 7. Is unit equivalent per meter square. Okay. You can check the margin here. Let's see question number 3. Answer number 3. Okay. Sigma here, 2.1. They round it up. Yeah. 0.6. Okay. 0.6 rounded to 1. 2 significant. Okay. Significant. 0.14 correct. Okay, so that is 0.1, not 0.0. I wrong significant figure rounding. Okay. The next question, the thread breaks, explain the initial subsequent motion of the ball. Okay, think about it. How will the ball move when the thread breaks? Under the effect of two forces, the weight and the electric force. But the electric force is not constant. It will decrease when the ball goes away from the wall, right? Wait. This is a uniform field. We don't know how the electric field will change with distance. when the ball goes away from the wall. We only know that this is a uniform field in the given diagram because the amount of charge of the wall is very high, very strong field. Okay, so we assume that the electric field is uniform, and therefore the electric force, the horizontal force, is constant. Okay, so if you accelerate in both directions, horizontal direction and vertical direction, it will speed up in both directions. Okay, the horizontal acceleration, of course, we can calculate by this force divided by the mass of the ball. Discussed, so it's 3 marks, so probably we need to do some calculation. Anyway, the math will say, yeah, we don't need to do the calculation, just describe inverse. Horizontal repulsive force and vertical pull gravity act on the ball, 2 forces. The ball has a constant acceleration. The motion is in a straight line. Yes, because the 2 forces are constant. So the sum, the total force, is also constant, and therefore it moves in one direction, straight line. Okay. And the angle 30 degrees to the wall, away from the wall, with the original line of thread. Okay. Initially, it was in equilibrium, meaning the sum of the 2 forces, F and mg, will be in the opposite direction with the tension, meaning the net force will be in 30 degree downward compared to the vertical direction. Okay, got it?
Yeah.
So that the sum of the 3 forces is the same. And therefore, when the thread breaks, it will move in that direction along the direction of the initial thread. Okay, so summarize the masking. The 2 forces, the ball is acted on by 2 constant forces. The downward, vertically downward weight, and horizontal electric force. The net force is constant, and in the directions, makes a direction of 30 degrees to the vertical along the thread. So the ball accelerates uniformly in that direction. One more question about charge here. Let's finish it. Also still question 3. And mostly paper 2 about charge, not very common about electric circuit. Okay, electric circuit usually common given in the paper 1. The center of the ball still carrying a charge of 1.2 times 10⁻⁶ coulomb, placed 0.4 meters from the point charge cubic. The charge on the ball acts as a point charge at the center of the ball here. P is the point on the line joining the charges where the electric field strength is 0. The distance PQ is 22 meters. Counting the charges on this big Q. So yes, of course, remember the significant figure. Okay, meaning 2 significant figure. The field to be 0. We've done this like 2 months ago. Okay. The field caused by this sphere Q times K over the distance, which is 0.4 minus 0.22 square, must be equal to K times the other charge at point Q here, which is wait. The center of the ball scalar charge. Okay, so this big Q already have the value 1.2, and we need to find this charge, state the value of the charge on Q. Okay, we need to find the charge Q here, and this Q is already given, which is 1.2 times 10⁻⁶. Okay.
I got 1.8 microcharge.
1.8 times 10⁻⁶, right?
Yeah.
Yeah, and also positive charge. Yes, correct. Over 0.22 meters square.
Is it actually?
Yeah. -6. Question D. 1.8 exactly. Yes, and 2 significant figures. as I mentioned. Outline without calculation whether or not the electric potential at P is 0. Is it 0? Zero.
No.
Yes. No. Yeah. Not 0. I don't know how to answer. No, because it may use yes for the right answer, but it's the opposite. But yeah, the field, the potential is not 0. Because the two just are the same sign, and they add the potential.
So the potential is two value, like.
You just add the potential of the two charges, which is Q1 over R1, and add it with KQ2 over R2. R2 is 0.22 and R1 is 0.4 minus 0.22. Okay, it's not 0 because the two charges without calculation, because they have the same sign. The charges are the same type.
So if the charge is one negative and one positive, it's going to be 0.
It could be 0. Depends on the
size.
distance. Depends on the distance also. For example, one positive and one negative. That depends on the value Q1 and Q2. Some position could be 0. Other position is different from 0. Okay. Just do the equation. This equation. So when the ratio Q1 over R1 is equal and opposite to Q2 over R2, the potential there will be 0.